Okay, we're back for another physics problem, and this one is page 680, number 22. You guys struggled with this a lot in homework last night. I'll admit that when I read through this one the first time, I also went, what? Okay, but I tried it out on paper, did a little thinking, and was like, oh yeah, okay, I got this. So I'll explain it to you guys as well. The problem reads as follows. A 3.8 kiloohm and a 2.1 kiloohm resistor are connected in parallel. This combination is connected in series with a 1.8 kiloohm resistor. If each resistor is rated at 1/2 of 1 watt, what is the maximum voltage that can be applied across the whole network? All right, so first it's just figuring out what they're saying. They describe a circuit in this problem that looks like this. They say that there's two resistors connected in parallel. So I'll go ahead and draw those, I guess, as being connected in parallel. I'm just going to label them R1 and R2. And then those two resistors are in series with a third resistor, R3. And I guess the numbers they give us are as follows. R1 is going to be, in my picture, 3.8 kiloohms. So 3,800 ohms. R2 is 2.1 kiloohms, which is 2,100 ohms. And then R3 is the smallest of the three resistors. It is 1.8 kiloohms, so 1,800 ohms. And what they want us to do in this picture, or in this situation, they want us to realize that when they say they're rated at 1/2 a watt, what they mean is that the maximum power for any resistor in this circuit is equal to 1/2 of 1 watt. So you're not allowed to have more than 1 watt of power through any resistor in this circuit. That's their goal. Anything that exceeds that 0.5 watts, and apparently the resistor will burn up. It can only handle so much current at such and such a voltage. Okay, well, what helped me out with this thing, first off, was having in mind a couple of things. One, I can take this circuit, there we go, and I can turn it into an equivalent circuit. So this problem has lots of things that we've been working on all kind of wedged into one thing. So I am going to turn this into an equivalent circuit. I'm going to turn it into this picture, where this is resistor R12, and this is resistor 3. Resistors 1 and 2 are connected in parallel. So I'm going to say that 1 over R12 is equal to 1 over R1 plus 1 over R2. So that means 1 over resistor 1, 2 is 1 over 3,800 ohms plus 1 over, I better extend that, 1 over 2,100 ohms. Now we know when these two resistors are connected in parallel that their combined resistance is going to turn out to be less than 2,100 and less than 3,800. If it's less than 2,100, it is less than 3,800, so I don't know why I'm telling you that. But the idea is that, yeah, that's going to work out. So I'll type in on my calculator 1 over 3,800 plus 1 divided by 2,100, and then I'll take the inverse of that, and I'll get that their combined resistance is 1,352 ohms. I'm just going to round that to 1,350 ohms. Okay? All right. Well, now looking at these two resistors and looking at this circuit, I'll change colors. This combined resistance is 1,350 ohms. This resistor by itself is 1,800 ohms. Okay? We know that power in a circuit has a bunch of different expressions. It is I times V, but it's also I squared times R, and it's also V squared over R. Okay, I'm going to make use of several of these all in one problem. The thing I know about this set of resistors would be a couple of things. One, R3 is connected to R1 and 2 in series. So whatever current flows through this also flows through this. I know that those currents are the same. Okay, so when I'm looking at that, the currents are the same, but in series the voltages are additive. So if I want to know how much total voltage I'm allowed to have over here, I need to know how much voltage this can get and how much voltage that combination can get. Well, when I'm looking at this, which of these two resistor messes would be the most, or is going to get the most power? Well, if they get the same current by power equals I squared R, this resistor, R3, is going to get the most power. It's going to use up the most power because they're both going to get the same current, but this is the bigger resistor. So this, R3, is my limiting case. As in, as long as I keep that one, resistor R3, as long as I keep that one using less than half a watt of power, then automatically this combination is also going to use less than half a watt based on it having less resistance. So what I'm going to do with this thing is I'm going to say, all right, I know that's the case. Let's figure out then, if my power is half a watt, how much current can go through this 1800 ohm resistor. Okay, so I'm looking at the 1800 ohm resistor. So I'll say that's supposed to be blue. 0.500 watts is equal to current squared times 1,800 ohms. And then I'll solve for that current. So again, I'll break out my calculator. I'll type in 0.500 watts divided by 1,800 ohms. And then I'll take the square root of that. And I'll get that my current looks like 0.0167 amps. Okay, now that's my current through all of this. So if I know the current and I know the resistance by V equals IR, I can also get the voltage drop across resistor 3. So V3 is going to be 0.0167 amps times my resistance, 1800 ohms. And again, this is just V equals IR. And I'll find that voltage drop 3 is 0.0167 times 1800, looks like about 30, maybe 30.1, depending on how you round, 30.1 volts. Okay. Now I just need to figure out what kind of voltage drop I have across resistor 1 and 2. And then I can get the total voltage drop across the battery, which is what I'm ultimately looking for. For resistor 1 and 2, I know that the current through 1 and 2 is the same as the current through 3 because this is a series circuit. So that is 0.0167 amps. The voltage drop then across 1 and 2 is I1 and 2 times resistance of 1 and 2. Well, the voltage drop then is I1 and 2, which is again 0.0167 amps, times a resistance of 1350 ohms. I plug those in. I see what I get. I'm betting something in the neighborhood of 24. Okay, 22.5, that works. So I get 22.5 volts there. My total voltage in this circuit then is V3 plus V12. So that looks like 22.5 plus 30.1, 52.6 volts, which, if we're looking at sig figs, yeah, we're probably looking at sig figs then, that's 53 volts. So that battery is allowed to be as big as 53 volts and nobody exceeds their power threshold. That is how you do that one. I like this problem. I picked this problem out because it made us think about power in different ways, because it made us think about where could you apply these series and parallel combination circuits, but maybe it was a little harder than I wanted. So hopefully you didn't struggle too much, and hopefully this helps out.